So now that we have looked at how tasks are actually implemented in Linux, let us look a bit more into how the stuff we have talked about for the past few lectures actually work. And these are basically fork and exec. And we have talked about the Linux philosophy of having fork and exec, and that fork basically copies the parent and creates the new child as a copy. And the way that fork is actually done, I mean, it would be completely stupid and completely redundant if you basically take the parent, copy everything that is related to the parent, as in basically copy the data that the parent owns, and then after 1 millisecond, after you have done that process, which is kind of expensive because it's 1.7 kilobytes of data that you're copying, and as we said that the kernel should be very efficient. So now that you have copied that amount of data, then the next millisecond or microsecond, you just remove them, delete them, and just load the new program. That's pretty stupid, right? Because you're basically wasting 1.7 kilobytes of data that you copied while they are completely useless. So the way that fork is implemented is that it uses a technique that is called copy on write pages. What happens when you call fork is that you start a process or a new task that actually points to the same data that the parent owns. So it doesn't copy the parent's data. It points to the same stack, to the same heap, it points to everything that the parent owns. And you mark it such that if any writing is being done in the child, if the child is supposed to basically use the exact same data and it's just a replica of the parent, then you basically start the copying process. Okay? Then you start making the duplication. But if not, if the child basically calls exec right after it starts, after the fork basically, then the data, the exec call will basically replace or will start a new clean structure for the child, and copy the new program right away to the child, instead of basically copying parent's program, removing parent's program, and copying child's program. So instead you just copy the child's program, and in this way you save quite a bit of both memory bandwidth or basically operations. I mean, it's not really memory bandwidth, but it's more operations that you're saving, and makes the whole process faster. Okay, so the fork is basically implemented in kernel/fork.c, and it is mostly memory stuff. It is mostly memory related work, and you find this very interesting note in the beginning of the fork.c class that basically says that fork.c contains the help routines for the fork system call. See also entry.s and others. Okay, because these are the different system, the different things that would help you to understand the system calls. Fork is rather simple, which it is, right? It's just, it has a few tweaks, but once you get it, it's right. Once you get the hang of it. But the memory management can be a C memory.c copy page range. So the hard part here is actually in the memory management. It's not the actual forking. Okay, and this is the fork.c program. It basically the stuff is actually done in. This is the real stuff. This is what actually does the stuff. It's __ do fork. There's another call that is called do fork, which is the real thing that you call. But this is where the do fork basically calls this function to do the real stuff. And basically it copies the process, and if successful, kickstarts it and waits for it to finish using the virtual memory if required. Okay, and you find that it's not an entirely easy read, but you can get the hang of it if you try to. I mean, it's not it's not the worst part of the Linux kernel that is written, and it is actually a bit documented also. But actually, do fork is not even the place. I mean, do fork does a lot of checks on the flags and on the on the states of the machine and on the errors. But the actual sweet stuff is even done in copy process. So you have a do fork that calls underscore underscore do fork that calls copy process. And copy process is, this is where the real meat is actually in the forking process. It basically creates the new process and a copy of the old one, but does not actually start it yet, because as we said, you don't start until you're scheduled basically. It copies the registers and all the appropriate parts of the process environment as per the clone flags. I mean, you have basically in Linux something that is called the clone flags, and these are the flags that control what is shared between the parent and the child process that is being forked. And the actual kickoff is left to the caller. So, and this is the caller basically. And then you have basically a long process that does everything that is related to actually copying the process, or making the replica of the process, managing that, doing the copy on write protocol, and so on. Okay. So the interesting work, as we said, is done in copy process, and this is basically a list of the things that copy process does. It basically creates a new kernel stack, thread infrastructure, and task structure for the new process. Right now, both the child and parent process are identical, because I mean it's just replicating it, and then it checks that the child is actually allowed to be spawned, because the child might be, as we said that during the class, you might have a limit on the number of children that this process can start, and you check that you're not exceeding the resource limits on the number of the processes. You set some initial values in the process descriptor in basically the task struct that you just created, and you set the child states to task uninterruptible to ensure that it does not yet run, because, well, task uninterruptible, as we said, will not run on a signal, for example. So it will just run when the event that it is waiting for happens, and that event is basically the actual creation of the child process, or of the child thread, or of the child task. Okay. You update the flags of the task structure, including, for example, things such as the if the process has not called exec yet. So this is again another flag that basically says that this process has not called exec, and that basically tells the operating system, the kernel, that okay, this process has not yet copied the data from the other program that it is supposed to run, and now if this process starts writing or reading, then I need to copy the data of the parent again. Then allocates a new PID to assign that new PID to the new task, now that the task is in a much better state. So I mean, there is a replica, but then now you have a complete structure almost for the task. You start giving the task an ID, a PID, and then you basically, as the scheduler tries to schedule things, I mean, there's a PID now for this, but it will not be scheduled yet because you have the task uninterruptible up. And then you basically, depending on the flags passed, you basically set up the sharing settings between the parent and the other and the children, or that child and other children of that parent, for example, siblings basically, and clean up and return the caller to the caller pointer to the new child. Now that the copy process is done, the do fork can actually do what it is supposed to do. And what the do fork tries to do is that it tries to run the child first. And the reason that do copy tries to run the child first, so I mean, once this returns, as we said that, well, you have do fork that calls this, and once that calls basically this here, okay, once you get P, you try basically to make P run before the parent. And the reason you do that is that you want to make sure that if P is going to call exec, then there is no need to copy to the data of the parent, because it might be actually problematic if the parent starts running before the child, and then the parent starts changing things in its own stack, or in its own basically data or flags, because that would basically mean that you also need to do the copy for the child, because otherwise the state of the data now is changed. So you need to make a replica at least of the things that are not going to be shared between the child and the parent. Okay, so then do copy basically runs the child first. There was there is a call that is called vfork, which is basically done also in do fork. I mean, it's again a system call that you can call, and vfork is much less used than forking now than normal fork, because the child executes basically. I mean, when you call vfork, you basically again use the same forking mechanism that we talked about, but using the flags. Vfork just raises another flag that basically says that this is not a normal fork, this is a vfork. And a vfork is a bit dangerous. Its semantics are not very safe. So you basically it basically starts but by the child executing as the sole thread in the parent's address space, and the parent is completely blocked until the child either calls exec or exits. So you be using vfork, you start the child and the parent gets blocked, absolutely cannot run until the child calls exec, and then the child basically will spawn the new program, or the child exits and then the child has gotten sole control over the parent's address space and the parent's basically task struct. Okay, and this should be used seldom. It shouldn't really be used, because there is usually a problem if if the child is supposed to call exec, but the child fails before it actually calls exec, and that basically means that the parent is blocked, and you have some uncertainty in your kernel that would be, that you can of course handle with basically some extra calls and stuff, but it's still, the amount of uncertainty and the amount of work that you would need to do to basically make sure that things are not broken is more than you would hope it would be.